All right. So within our stoichiometry, right, stoichiometric relationships are really just the relationships between the moles of one thing and the moles of another thing in a chemical reaction, okay? So we always want to start with a balanced chemical reaction, right? And generally, right, when we have a precipitate reaction, we want to start from the balanced net ionic equation, okay? But in our complete ionic, we have our extra other ions. We would want to make sure that we draw them when we draw the particle representations, okay? So within our stoichiometry here, what I'm going to do is I'm going to use a different reaction, okay? So if I had copper 2 plus, that was aqueous, and two hydroxides, aqueous, they could form copper hydroxide, okay? And this would be a solid. So if I had a question that asked what volume of 0.2 molar copper sulfate is required to react with 500 milliliters of 0.1 molar NaOH. Okay? Well, I would look at this question and I would say, well, in my equation, I don't have copper. I have copper sulfate. And in my equation, I don't have hydroxide. I have sodium hydroxide. But from these two, right, these two molarities, I can calculate what the concentration of hydroxide would be. Sodium is always soluble, so sodium hydroxide is soluble. Copper sulfate, right, we don't actually know from our precipitation rules, but copper sulfate is soluble as well. So what we are going to do is we're going to say, if I have, right, 500 milliliters, I'm going to write that 500 milliliters, I'm going to convert that to liters, so 1,000 milliliters to 1 liter. And then I have my concentration of NaOH, right? I have 0.1 moles of NaOH per 1 liter. But in my equation, right, NaOH splits up, right? I can draw this. NaOH splits up to Na plus and OH minus. So my stoichiometric relationship is 1 to 1. I have 1 mole of NaOH to 1 mole of OH minus. Okay? Then I can start using my other equation here. Okay? Now I see, okay, for every 2 moles of OH minus, I want 1 mole of Cu plus, 2 plus. 1 mole of copper, 2 plus. Okay? So then, right, now I have my moles of copper 2 plus. My copper 2 plus, I have 1 mole of copper 2 plus is 1 mole of copper sulfate, or that's coming from 1 mole of copper sulfate. And then my last piece on here, right, is going to be getting to my volume, and I say, well, I have 0.2 moles of copper sulfate. Well, I'm just going to barely fit it on here per 1 liter. And then I just need to do my calculation, right? 500 divided by 1,000, that's 0.5, times 0.1, that's 0.05. Divided by 2 would be 0.025. Divided by 0.2 is my last piece. So 0.025 divided by 0.2, that would be the same thing as times 5. I think it should be 0.0125, right? Which would be 125 milliliters, right? Let me just see if I did that correctly on my calculator. Looks like I did. That would be 0.125 liters, which would be 125 milliliters. Okay? So what we see is that every single time, right, I'm using my stoichiometric relationships, right? My copper sulfate, I can write the reaction, breaks up into Cu2 plus and SO4 2 minus, right? These equations up here, right, are all of the equations that I need, and I need to use the mole-to-mole ratios within those equations. So if I had copper hydroxide, right, I would get 2 hydroxides for 1 copper, okay? So we have to use our stoichiometric relationships, okay? All right, let's flip over to the next page. All right, so if we have our next page here, right, what we're going to talk about is our acid-base reactions, right? Acid-base reactions are all about hydrogen being lost or gained. Okay, so a couple of things that we need to remember is that acids are going to form H plus in water, right? Hydrogen, any sort of acid loses H plus, okay? So acids lose H plus, or they're going to form H plus when they get into water, okay? So we're going to talk about doing lots of reactions in water, right? So a strong acid, right, like HCl, when we put it in water, is going to form H plus and Cl minus. So I could also write this, right, as HCl plus H2O forms H3O plus and Cl minus, okay? So we have a few different strong acids, okay? So our strong acids are HCl, HBr, HI, and then we have a few other ones. So first off, what we'll notice, right, Cl, Br, and I, these are all our halogens, right, except for fluorine. HF is not a strong acid, okay? Our other strong acids would be HNO3, H2SO4, and HClO4. Okay, so perchloric acid, sulfuric acid, nitric acid, iodic, bromic, and chloric acid, hydrochloric acid. Okay, so we will kind of need to memorize those 6 again, right? But it's not too bad to memorize these 3, and then these, right? These 3 acids, they all have a certain reason why they are stabilized and why they're strong, okay? We'll talk more about these later this year, okay? But, right, we will need to, and we will also talk about weak acids later this year, okay? So weak acids do not fully ionize, okay? So strong acids, they're completely going to go over this way to form H plus and Cl minus. Weak acids do not fully ionize. Okay? And we will talk a whole lot more about that later this year. Okay? But if we look at our reactions, right? Let's just take this one up here. Okay? We see HCl plus H2O forms H3O plus and Cl minus. We can label this as acids and base pairs, okay? So HCl is an acid, right? And it's going to form H3O plus, right? We know that we are forming H3O plus, so H plus loses the acid. So the other piece that is accepting the acid is H2O. H2O in this case is acting as a base, okay? But our conjugate acid is H3O plus, and our conjugate base is Cl minus, okay? So the acid, HCl, loses H plus, it has a conjugate base after it's lost that H plus. The base, H2O, has a conjugate acid that could lose H plus, right? It's gained that H plus now, it could lose it and come back to be the base, okay? So this is kind of an introduction to our acids, right? Same idea with our bases, okay? So bases, right, we are going to form OH minus, form OH minus in water, right? So an example of this would be NaOH that goes to Na plus and OH minus, okay? But we could also look at something like NH3. When it's put in water, right, it's going to actually pull one of those hydrogens off of water, and it's going to form NH4 plus and OH minus, okay? But again, we can identify our acids and bases, right? In this case, H2O lost an H plus, so it's an acid, and OH minus would be the conjugate base. NH3 is acting as a base where it's accepting H plus, and then the NH4 plus is the conjugate acid, okay? So this is the Bronsted-Lowry definition of acids and bases, okay? It's all about where the hydrogen goes, all right? We'll come back in a second.